Yep. Everything fine? Can you hear me? No. No. Well, you yes, but hello? Oh, okay. All right. So my name is Delio. I'm just checking if I can. Okay. See the presentation. All right. So my name is Delio, and I'm going to present. I'm going to do this talk, which is called "No Country for Old Mangoes." And well, of course, I'm not going to talk about fruit, but Mango is a library, of course, written in Go, because I mean that's the language we all love here. And at the moment, we don't use this library here, but it's something which I used in order to build like a complex system in the past. And I really like this kind of say networking, or this way of creating distributed systems. So actually, I used it a bit also here, but very slightly. So let's start with distributed systems. I guess, like amongst you, there's people with different degrees of knowledge and, not only about Go, but also about programming in general. So, I mean, the thing is that let's start using some definition which are a bit loose. So, for example, for distributed system, we're going to say that the distributed system is just system and is spread across different logical unit. I'm not talking about anything physical. That's the most important thing. So let's see where we are now with distributed systems. The first thing we can see is when we first think about distributed system, what comes to our mind as first is, oh, I'm going to build a project which is going to have, I don't know, in the past maybe had been built with SOA, not anymore. You might think about microservices, any other kind of architecture, or you might, I don't know what's your background, but you might have done something with actors, which is something interesting that we will see a bit at the end. So the first thing that comes to our mind is that when we make a distributed systems, we generally have something which is made of different components. Now, let's see a bit how generally we implement such a system. So most likely we're going to have something synchronous, and the most used approach is to have REST services, even though that's not what I like most. Then, I don't know if somebody has used here gRPC. Yeah. And then somebody might use Thrift. However, you can see that the most of these techniques are all synchronous. When people think about something asynchronous instead, they start using something like a queuing system. So we have wrapping queue, nuts, or streams. Now, what is the key difference between these specific synchronous ways of creating your distributed system and these asynchronous ones? The thing you can see is that all of those asynchronous ones are based on a broker. So always in all those cases, you will have either your RabbitMQ or whatever your instance, and it will be based always on a broker. What we're going to see today is how to do things, but without a broker. So this is what we have now, and let's go one level higher. So first of all, of course, when we have a system like this, we can see it as a graph. So we have like all our nodes, and they're going to be our services or something else. And then we're going to have the edges which connect them. Now, let's see how this gets translated in what we're going to do now. So let's introduce the first jargon. So I might use words that you've been using in a different way, and we will see straight after this slide. But however, a vertex in this case, I will say that is a socket. Now you can see it as a socket, like an electrical socket, which can, get, not only give electricity, but receive electricity. And then we have a transport. Now transport, in this case, we have this plug, which of course is wrong in this case. Has three, I chose it in purpose. Yeah. So these are the key thing. However, there is one more that I didn't put in this slide, and we will see it right away. So, what is a transport? Um, transport is something which we use in order to transfer this data. However, we don't know what is transferred inside. In our case, it's always going to be bytes. However, generally, one of these transport works just transferring this data and has, some specific characteristic, but doesn't tell us where things go and how they go somewhere else. So, for example, here, of course, we have a glass and we have a straw, and we don't know what's inside. All we know is that this straw will take something from the bottom of the glass and will put it up. In the other case, we will see all these tubes, all these pipes, and we only know that these are pipes, but nothing tells us if these pipes are gonna, distribute water or whatever it is in different places, or just is a one-on-one connection, anything like this. What I didn't mention before is actually the protocol. Now, this is the specific thing where I tell you that I'm going to use this word in a different, with a different meaning than one you're used to. So I think you already have in mind what the protocol might be. I don't know if somebody wants to say the name of a protocol he might think about. No. Wait, we will see in a moment. What you see here, that we have, for example, this water here, which is distributed all across the field. So essentially, this is a kind of protocol because it's distributing the water, which is all the same in the whole field and not in a specific part of the field. While a different protocol can actually may communicate one person with another or one person with multiple people. So keeping this in mind, let's see what transports we have. So again, our pipes here, and these are our transports. I mean, they're common transport that we generally use. There is, however, one of those that is not transport. And I mean, if you see all this list, you might tell me later what you think, which one you think is the intruder. So I guess everybody's confident with TCP, UDP, etc. Maybe, I don't know if anybody knows what is improc and IPC. Anybody? No? All right, so let's see these two specific ones. IPC is inter-process communication. It's something that most likely you haven't been using when you've been developing, because essentially you might have two different applications running in the same machine, and this is a way to let communicate two different applications. So there are two different processes running in the same machine. You're not going to be using it often, or you haven't been using it at all, because generally now all your systems are distributed across. Maybe you're deploying them on Kubernetes, so they're going to be different pods, so you can't use actually you could, but that's not the way. So I haven't been using it, and generally nobody uses it anymore. However, improc is a bit more important. It might be a bit loose with the definition of a distributed system, but improc means in process, which means that we are letting communicate different entities in the same process. Now, the first thing that could come to your mind essentially is threads or something like this, and effectively is this. So, because we are using Go, most likely, I mean, actually, you might guess, and it's right, we are going to use, not us, but what I'm going to use is going to use channels and the Go routines. So we're talking about something which is, yes, spread across, but the same process. So now let's see the protocols. Now, you might have thought, as I was asking before, that as a protocol we would have had TCP or HTTP, but actually those were the transports. And here are the most common protocols. Now, we will see not all of them. I have here rec, read, pub, sub, push, pull, start, etc. We don't have all these protocols in the same library, but I put them just to show you that there is quite a lot of different protocols. Some more common, some less. Now, let's see, yeah, Mongoose. So I don't know if anybody of you has used something like ZeroMQ. Yeah. So essentially, Mongoose is a library like ZeroMQ. It's actually the child of ZeroMQ. Has a like kind of bad history. I mean, how it got created. However, Mongoose is written totally in Go, it's in pure Go, and implements something called the scalability protocols. Now, we got quite a few kind of libraries of the same way. They generally are just networking libraries. Now, what we generally think is that we want to use things like Kafka or any broker system because it's easier. Now, I can't say that doing things the hard way is easier because it wouldn't be hard otherwise. But this kind of library actually helps us a lot. Now, the first library we actually has been built in order to solve problems of having a distributed system but without a broker was ZeroMQ. However, then there's been something more standardized, even if it hasn't been actually adopted much, which are the scalability protocols with several implementations. And Nano Messages is the first, and then Mangos is actually the implementation in Go. Now, the key difference I like to stress between ZeroQ and Mangos or generally scalability protocols is that they have an open API. So if you don't like something that you see in the library, you've got a way to extend it. You might think about a different protocol or a different transport. Maybe the maintainers will not provide it for you, but it's very easy actually to implement those things. While with ZeroQ, you can't do that. So there's advantages, pros and cons about all the libraries, so ZMQ and scalability protocols, essentially the adoption. But you know, here we are talking about Go and Mongoose. So let's see one of the first protocols here. Actually, you will see that I have rec and rep, which are two protocols. But why do I put two protocols at the same time instead of just one? So generally, if I want to transfer some data, I will have always something which will send and something which has to be able to receive. If the two entities are not able to communicate, to talk the same language, they won't be able to communicate. So you actually can mix and match several protocols, but the rec and rep are like a couple. So we will see other couples later, but this is like the most simple one and also the one that you should use less possible. So recrep means requester and replier. Now a requester is a socket, a replier is another socket. How it works is that a requester is going to request information and the replier is going to reply. Now, how do they actually act? A requester will have a state machine as well as the replier. Now, a requester will be in a specific state, which is I've sent a message. The moment it sends a message is in the receiving mode. So if you try to send, for example, two messages, it will not work and it will return an error. So every time you have to request and then wait for a response. While the replier will start with reply, with like listening for a message, accepting a message, and then will then reply. Now, as you can see from this code, the library is actually quite easy. It's not much verbose. So we have request socket and an error, and we have just this simple function called new socket. I don't know if you can read well anyway, yeah. So what we do in this case, we have on the left the replier, which will listen to a URL, and then will wait for a message to come, and then when it arrives, it will reply back. So this is quite actually easy. And as you see, when we send a message, the message is going to be an actual set of bytes. We're sending a date, and that's it. Now, what we have to bear in mind here is that one socket is essentially one specific process. So when we are sending messages, is always like one node sending that message. So it's nothing to do with like what we have with the HTTP connections and you know, anything that we do in REST. Actually, it's a bit like more difficult to do it this way. Now, let's see, however, what is the other characteristic of this library. So first of all, when we, as you've seen before, when we create a socket, then we have to either listen to a specific URL on a port, like we do with a normal server, either we have to dial in to another URL. Now, bear in mind that this is not something that, only a requester can listen to something. You can do it either way. Doesn't matter which socket listen and which one actually dials in. It's exactly the same, they're normal sockets. Now, if you see here, we have 2 replier and 3 requester. Now, as you can see, we have one request goes into the replier and back. Now, what happens in this situation that you would think at this point, oh, let's use it as a proxy, for example. But going a moment back here, you know, I put some specific connection, and we see that this requester at the moment is only sending information to this replier. However, that's not true. What this library gives us is the possibility for the requester to dial in 2 different repliers, and it automatically load balances the request. So we can have a lot of repliers, and one requester starts pushing messages to the replier, and they will actually return with the right message. Now, the reason why I say you can't use it as a HTTP proxy, I mean, you can, but not just simple as that, is because an HTTP request will come from several different users, while you should have a new socket every time you want to communicate with your replier. However, there is a solution. In order to let you see, however, how this all works, I just prepared a bit of code and I'm going to show you. But it doesn't work. Trying to share. And, oh. So, see here. All right. So, let's start with so here we go. And so essentially what we do with this request, we are creating a requester. So we create just one requester and we create a pool of repliers. Now, I'm not sure if you can see exactly the URLs. They are just improc URL. Oh, I clicked on the all right. All right. So as you see here, I'm creating a requester, which is in a routine, and so it's running at some point, and I have actually here a set of URLs, and I'm going to create some replier for all these URLs, which are 1, 2, 3, and 4. Now, the requester, what it will do is will just send 4 messages, and it's going to wait for the messages back. Now, let's run it. Now, what you see is that the requester 1, because the requester is just one, has got a name, received a message, which is the replier in URL 1 greets you, oh, RQ1. Now, of course, we have only one requester, so we will always see that they are all the reply, they're replying to requester 1. Now, you can see that the message has been spread across all the different repliers because we have 1, 2, 3, and 4, and then again 1. Now, what do you notice here about the order? Anything specific? We know that everything should be asynchronous, but actually here it doesn't look like. And if I repeat it, again, it won't be 1, 2, 3, 4, and 1. The reason why, and this might surprise, is because if you think about it, is that we said that there are states in this request and reply. So the requester has to send a message and then has to have it back. So generally, the library will just share across, but will not send any new message to another replier if hasn't received the first one back. However, we can do something about this. But before doing that, let's do a small change. Let's add a second requester, and I will show you something that's interesting. So if I clear everything here and I run it, well, you will see that requester 2 received from the replier 1, oh, I greet you, requester 2, and everything is matched. So essentially, automatically, if I send a message to a specific replier, the replier knows who I am and sends a message back to me. So there is no problem here on understanding when we have different, even if we were doing it in a really asynchronous way, there is no problem in sending back the message properly. However, we don't want things, of course, all like always 1, 2, 3, 4, 5, but we want to try to experiment with something which is really asynchronous. So one thing that Mangos gives us is the context, which essentially means when I make a connection, I can open a new context. So it's still the same connection, but I'm like a sub-user of this connection. So if now I run the code, you will see that I will have 3, 1, 2, 3, 4. I run it again and have 2, 3, 4, 1, 1, for example. The code here is a bit complicated. I'm not sure if you want to see it, but the only difference is that here, instead of just sending a message, first we use a go routine. We have a context which we get from open context, and then we use the context as we would use a normal socket. And even as you can see from here, again, rec1 returns from rec1, URL2, and so on. So always they're matched. There's never a problem when a replier sends the message to the wrong requester, which is what we want. Now, I stop sharing here. No. I need to stop sharing. Oh, oh. I can see it. Okay. All right. So, where are we? In the presentation. So, next step. So we've seen this request and replier, and now we will see a different set of protocols. Are we? No. Okay. No. Not sure. All right, PubSub. Now, you might, of course, know what PubSub means in this case, where you just have a publisher and a subscriber. Now, if you see, they work exactly the same. I mean, the way we create the socket is exactly the same. Just in this case, while a requester was only requesting to one replier at a time, with the PubSub is the situation is different. We have a publisher which just diffuses the messages across all the subscribers. Now, let's see this. So we have a publisher gets into both subscriber, and of course we have a different situation where we have actually two different publishers and three different subscribers. So this means that we can have a multiple instances of the same publisher and subscriber. So if we need to give, we have something which needs more memory, or we can do it. The only thing that we have to mind is that every time we introduce a new socket, we need to make sure that there is either a dial-in, either a listen to for them. Other one is push-pull. Now, do you know what is the difference between push-pull and PubSub? So, No, the connection in this case are always open. So this is never something like in HTTP. Well, HTTP2 is not like that, but you're never going to do a request and then closing the connection. That's the whole point. We are always keeping the connection open. The difference between pub sub and push pull is that while a pub has some connected subscribers and publish it to all of them, a pusher just pushes to one. Essentially, a pusher is like a requester that doesn't care about having any response back. Might say, why? Well, if we want something which is asynchronous, we might not care at all about any response, and then we might have actually a system where we have in the same service a pusher and a puller to receive the message back. So we have it totally asynchronous. That's the whole point. However, with the push-pull and the pub-sub, we can do some kind of, we can aggregate them to create something more interesting. But first, here in push-pull, we can see that essentially the difference is while with the pub-sub, we are just sending to all the subscribers. Here, we are just load balancing like with the rec. And here we have the same thing as we've seen it for the pub-sub. Okay. So now protocols are actually many, and so there are other here, the bus, which is actually called also router, and the surveyor. Now, these are available only in Mangos. There is a star, which is available only in MSG, but it's not very important. I mean, unless you need something very specific, you know, most of the time you're going to use essentially public sub. And that's what actually Kafka has. So notice one thing, I couldn't create code for that, I didn't have time, but if you are using a request and a replier, if the replier drops, well, when it goes up again, the requester will send a message, so you don't lose anything in this case. That's important. While for the pub sub, you have the problem that you might lose messages, and this happens only if the connection drops. Otherwise, you don't lose anything. Now, let's see the transports, because for now we see only the protocols. Here is actually very, very simple. So how to load the transport? You can see it from here. You just have a naked import. In the past, it was actually much more not difficult, but was a bit more verbose. Now we just add all the transports, and that's it. And what we have here, improc, IPC, TCP, and then together with TSL. So let's see. Now, the ones we're going to focus on at the moment are just TCP and improc. Why? Because the most of the system you're going to create, generally they use TCP. So they go over the net. And so this is the way actually how you will contact. See anything? I'm not sure. Okay. So this is how you contact TCP socket. You just have a dial and you just specify the URL. Because of the TCP, the system already knows that it's TCP. If you want to use something instead that is improc, you will just put improc as a protocol. Actually, this is a transport, but we used to call it protocol. So that's it. You can put whatever you want. It doesn't have to be www or whatever .com or anything. So it's pretty simple. Now, let's create something a bit more complex, and is this. So you can see here we have a pub socket, which goes into sub and into another sub. Now, this service that you see here actually is a service which contains only one socket and is a publisher. Here instead, you have a service which includes a subscriber and a pusher. You will see that the publisher will publish to both this subscriber, and each subscriber will actually push to only one of the two pullers. And this essentially is exactly what Kafka is doing now. Now, I can say that you use this library and you have everything working exactly as Kafka because there is something else, but you know, you can create this kind of topologies, as you see, quite easy. Now, what do we have as a transport between all these services? The first thing you see is, okay, we have everything distributed and we have everything, for example, deployed on Kubernetes. You have different pods that we're going to use TCP. However, we could mix them up. So, for example, I have here a publisher which is publishing things through TCP to another service, and then the service will use improc and WebSockets in order to contact different other services and so on. TCP, improc, IPC. Of course, when you see something improc means that this specific service actually should include also this pooler here in the same actual process, which you might think that is unuseful, but I will show you in actually a moment why it is not. So, but why? Let's think of a monolithic app. Now, in this case, we can create monolithic apps in sort of different ways, but we always thrive for having things which are componentized and totally separated in different domains. So if we have this monolithic app, which is actually may build upon different components, we can actually see that we could have this sort of connections. Now, this is the same process, and we could actually use improc in order to communicate inside the same application. In fact, we should have it. Yeah. One more. So the reason why we say like, okay, we have all this connection inside the same application, which makes things a bit more complicated, is because the moment we want to actually spread things and break them apart, we can actually keep the same code, but instead of using in memory, so in process communication, we just go next level. We break this component, we put them in different services, and there is a minimal code change because you go from one monolith to distributed system. Now, if we see this as the only way of breaking things apart, that's not true. Because here we have two different blocks. So many times, like all applications, you would have the same application, you repeat it, so you have your first instance, and then the whole app is in a different instance. And when you actually are building a system with an API gateway, you have two different instances of API gateways, and you will have load balancer. And let's go through this one less, I think. Yeah. So what we see here is that our load balancer will choose one API gateway, and the moment it goes into an API gateway, we can only go to, for example, a specific instance of our monolithic application. So if we want to distribute it, the first thing that we think we can do is, okay, let's create another instance, and the load balancer might actually go through this different route and go to this other monolith. We know that this is not the best situation. However, if you do something like this, we can see that actually the component one, we see that has an improc connection with the component C, but it can actually contact over TCP the component 3 of the other instance. And this is what happens generally with the akka framework, and so with the actors. Now, we haven't done anything here with actors. These are not really actors, but this is just a way to show you how actually, in principle, this works and how we can benefit of it. And this works over, of course, also the other way around. So we can see that C3 from this instance can actually contact C4 from a different instance or in the same one through improc. Now, let's see what is actually the problem here. Did it go through? No. Next one. Okay, let's see. So, okay. So one of the problems now we have is that if we use something like Kafka, we know we have one URL and then everybody will register. We use Zookeeper, for example. But how do we know how to contact the different services, also especially at runtime? Because many times we want, for example, a new pod to go up and has to be connected to all the request reply or whatever we want. So we have several solutions. The first one is configuration is static, but of course is not the ideal one, because this way, if we create a new pod, how on earth are we going to know where the new pod is? Then Kubernetes. Generally, you're used to use Kubernetes just using the service discovery, which expects you to use HTTP. However, using the actual Kubernetes client, you can get all the pods. So one way you would have, I didn't use this solution, is to get all the pods and every time, get a connection. But the solution that I used actually in the past is to use console. Now, console has quite a lot of advantages. It can actually notify you of any change. And so essentially, every time a service goes up, will first of all say to console, oh, hello, I'm here. And so we'll notify the console of its existence. And then every time somebody needs this specific service, we'll actually contact console and get all the pods or whatever it is using Kubernetes. And so this is actually the way I've built a system. And let's see now here. So we are ready for with all these things that you've seen to go. If you want to use this library, if you don't, there's no problem. But I mean, I really enjoyed working with this library in the past. But before you go, so what happened here is a bit of advertisement. So I've been contacted in the past, actually recently, for writing a couple of 3 actually chapters of a Go book. So if anybody's interested, depending on exactly on how much you know Go, this is like just a course book. So there's a lot in there. There is also a live course, and so it might be beneficial or not, depending on your situation. So, questions? Yeah. There is a yeah.
So how does that work?
I have no idea.
It's fine. Okay, great. So if I understood right, with zero MQ that you have right now, all the packets?
No, zero MQ is just like
sorry, Mango.
yeah, mangoes.
Great. Yeah. So if you have different process, or you may implement an actor model or whatever architecture
Yeah, it's not really
you want.
Yeah.
Okay, you use this in order to easy change your way that you communicate with these services. I mean, you use it in order to just wrap around this complex of networking, or also because you want dynamically change the transport layer.
So
For example, let's say that you have a service that's run inside the mini monolithic thing. Let's say a subscriber side. Okay. So, and you want to change, you want to scale somehow, and you have it in another machine. So you can do it in runtime, let's say, and change the traffic from in proc to maybe TCP or something like this.
Well,
You use it like something like this.
well, I haven't used it this way, but actually it's possible to do it at runtime for the simple reason that you just need to have something like console, for example, so that you can be notified. Because, for example, what I do is, I need a set of subscribers, for example, or I need a set of requesters. So it would be possible actually to do it at runtime, because I can be notified somehow that there is a new requester. And to me, it doesn't matter if the requester is in the same process or is somewhere else.
Okay.
You can have even a small bit that can be extracted.
So, sorry, another one about this. So you use it in order just to hide this complex loads of networking with this package.
Is not just to hide. I mean, this is just one aspect of the fact that we can change. The other advantage is that I can create a topology and say, oh, I want a publisher and a subscriber, and I don't need to have them in different processes. I can actually build even a monolithic app, which is not going to be an actual monolith again, but one single process where all the components are actually independent. They run as independent sub-processes. That's the way. So it's easy actually to organize the code.
Okay, cool. Thanks.
Anybody else?
Boom. 1, 2. So I don't know if I understood correctly, but previously you said that we use tools like Consul or Kubernetes or configuration in order for a component to find where different request listeners are located, correct?
Yeah.
So this is a centralized point where we can find everything, right? So how does this differ, or how does this is better than using a broker, which is essentially a centralized point as well?
Well, so the difference is, first of all, that you don't need you don't need decentralized point. It's up to you. I mean, this is just a way to get it easier. The key thing is that yes, you might have to need in order to have something very dynamic, a central point, but it's not going to be contacted every time. So, for example, if you have to contact Consul I was using it with gRPC, for example. So every time I had to make a gRPC call, I had to request Consul, oh, please give me one of the available pods with the actual server. In this case, instead, what you do, you call it at once, and you get all the available pods. And hoping that no pod goes down, you just keep the connection open, so you will not have to contact any again Consul in order to get the pods. Actually, you know exactly when a pod goes down because the connection drops. So you don't need to contact continuously. I mean, you can still cache it. I mean, it's not a big deal, but you don't have to do it every time. This doesn't mean that every broker system is bad, but if you want to do something brokerless, this is an option, first of all. Anybody else? All right. Well, so let's see. Thank you.